Hey guys, today we're going to essentially do stoichiometry, which is balancing chemical equations. Chemical equation is simply a way of representing a chemical change, where we are going from one group of chemicals called the reactants to another group of chemicals called the products. And the main difference is really how the arrangements of each elements are bonded to each other. And a way of representing this chemical change is through a chemical equation. Now, essentially, the way of writing a chemical equation is simply on the left side you will have your starting materials or your reactants. Then you'll have an arrow going from those guys toward your end materials or your products. And the key of balancing a chemical equation is the law of conservation of matter. Essentially, we're not going to be losing any particular element. So if on the reactant side we have, say, 5 atoms of silver, we're going to need 5 atoms of silver on the product side as well. And here are just some examples of what chemical equations look like as far as writing out the products and the reactants that they came from. Now, the problem with these groups of guys is that they're not balanced yet. So let's work on actually balancing or working with stoichiometry. So for any chemical equation, first thing to do is just look up how many reactants and how many of each element you have on the product side. And for this equation, it's pretty simple. We just have Ag, which is silver, and we have S, which is sulfur. Right from the start, let's count up how many of each element we have on both sides. Well, on the left side, for the reactant side, we have 1 silver, and for the product side, there are currently 2 silvers. Since we have this subscript 2 here, that subscript means that the thing to the left of it, that's how many we have of that. Now, in regards to sulfur, on the reactant side, we currently only have 1, and on the product side, there is no subscript to the right of sulfur in silver sulfide, therefore we just have 1 there. Now, next thing to look for is which, if any, elements are not equal on both sides. Well, currently sulfur is equal on both sides, but silver is not. We have 1 silver on the reactant side, and we have 2 silvers on the product side. So to basically balance this, we're going to need to add coefficients. Coefficients are added at the beginning of a chemical compound or a element in a chemical equation. And essentially what a coefficient does is it multiplies every number of element part of that individual compound. So for example, let's say what happens if we add a coefficient of 2 in front of Ag on the reactant side. Well, now that essentially multiplies the number of silver we had by 2 on the reactant side. So now that number on the reactant side becomes 2. And we don't need to add any other number for any of the other compounds. Essentially, if the coefficient is 1, you can just leave that blank. And now what we see is that we have 2 silvers on both sides of the equation and 1 sulfur on both sides of the equation. So because we added a 2 in front of Ag on the reactant side, our chemical equation is now balanced. Going on to another example for, say, the rusting of iron in the presence of oxygen. Well, right from the start, let's just count up how many of each element we have on both sides. On the reactant side, we currently only have 1 iron. And on the product side, for iron oxide, that's Fe2O3. Therefore, each time we have iron oxide, we're going to see 2 irons. And since we are working with molecular oxygen on the reactant side, which basically means that that's oxygen with a subscript of 2, that means that there are 2 individual atoms of oxygen on the reactant side currently, and there are currently 3 atoms of oxygen on the product side. And this is without adding any stoichiometry or stoichiometric coefficients. Now, what we can see is that both iron and both oxygen are not balanced. So we're going to have to work on a way of balancing these guys. Now, one thing to note is that on the product side, no matter what, we have oxygen, we have iron oxide, which is O3, And on the reactant side, we are working with O2. Now, whatever coefficient we add at the beginning of O2, it will always be an even number of oxygen. However, for iron oxide, we could see a situation where there's an odd number. So the easiest thing to do is simply try to get an even number of oxygen on the right side first. Now, what I did is I added a coefficient of 2 in front of iron oxide. That multiplies the entire chemical compound by 2. Therefore, instead of having 2 irons on the right side of the equation, we now have 2 times 2, which is 4 irons, and we now have a total number of oxygen of 2. That coefficient 2 times the subscript 3, which would be essentially 6 total oxygen on the right side of the equation. Cool. We're not balanced yet, though. So the next thing we can work on is, say, just balancing the irons and the oxygens on the reactant side of the equation. So if we have currently 4 irons on the right side, then to get 4 irons on the left side, we just need to add a stoichiometric coefficient of 4 in front of Fe. And that brings our total number of iron to 4 on both sides. Now for oxygen, we're going to need to add a stoichiometric coefficient that essentially adds up to 6 total oxygen. So if each time we have a coefficient in front of O2, that's adding 2 oxygen to the left side of the equation. Therefore, what times 2 gives you 6? Well, 3. So essentially 3 times 2 is going to be 6. And now we have a balanced chemical equation because we have 4 irons are accounted for on both sides of the equation, as well as 6 oxygens. Therefore, the balanced chemical equation is 4Fe, 3O2, yielding 2 moles of Fe2O3. Going on to another example, which would be essentially a chemical equation that's pretty common in organic chemistry, but definitely not one that you want to experience in life. This seems like a bear at first, and that's okay, but let's just start out with how many of each element we have. So for Hg, or mercury, currently on the left side of the equation we are seeing 1, and on the right side of the equation we are seeing 1 mole of Hg as well. Now as far as sulfur, this one, since sulfur is only appearing in H2SO4 on the left side, that molecule only has 1 sulfur, and on the right side we have HgSO4 as well as SO2, so they each have a sulfur atom. So that would add up to 2 sulfurs on the left side, on the right side of the equation. Now as far as the number of oxygen goes, for the left side of the equation we have 4, and on the right side of the equation we have 4 from HgSO4, we have 2 from SO2, and then we have 1 from H2O. Therefore we have 4 plus 2 is 6, plus 1 is 7 oxygens on the right side of the equation. And now what we have for hydrogen, the last element, is we have 2 on the left side of the equation, and we have just 2 on the right side of the equation. So this chemical equation seems like a bear so far, and that's true. Now, one thing that we can do is, usually as a good rule of thumb, oxygen and hydrogen, that's something you want to try to balance last. Usually they're in a bunch of elements or a bunch of compounds, so if you balance out the other elements first, then normally that helps balance out oxygen and hydrogen along the way. So mercury is already balanced, Hg. So let's go on to sulfur. If on the right side of the equation we have 2 sulfur atoms, on the left side of the equation, sulfur only appears in the molecule H2SO4. So what coefficient could we add that would essentially give us 2 moles of sulfur on the left side of the equation? Well, if adding a coefficient in front of a chemical compound multiplies everything in that particular compound by 2, or by whatever the number that coefficient is, if we want to get 2 sulfurs, let's just add a 2. Therefore, on the left side of the equation, 2 times 1 sulfur is now going to be 2 sulfurs. However, that also modifies the number of oxygen and hydrogen we have. So if our molecule of H2SO4 has 4 units of oxygen and we just multiplied that by 2, 4 times 2 is going to be 8. And then as for hydrogen, we have 2 units of hydrogen for every H2SO4, and we just add a coefficient of 2 in front of that compound. Therefore, 2 times 2 is going to be 4 units of hydrogen. So now what we have is we have a balanced amount of mercury, we have a balanced amount of sulfur, and now what's left is oxygen and hydrogen. And it looks like we have 1 more oxygen on the reactant side and 2 more hydrogen on the reactant side than we do on the product side. Well, then this is a pretty simple fix. H2SO4 is a molecule that has 2 hydrogens H2O is a molecule that has 2 hydrogens and 1 oxygen. Therefore, if we want to add 2 more hydrogen and 1 more oxygen to our product side, we just need to add a 2. Therefore, essentially, the total amount of oxygen we have now is 4 plus 2, which is 6, plus 2 times 1, which would be 2. So essentially, that's going to be 6 plus 8, so a total of 8 oxygen. And now what we have on the product side is hydrogen, which only shows up in water on the product side, and we have a coefficient of 2. Therefore, 2 times 2 is going to be 4. So there we go. This, what seemed like a complex equation at first, is actually not that bad as long as you take your time. Because for this equation, this complicated looking equation, all we had to do was add a coefficient of 2 to H2SO4 on the reactant side, and add a coefficient of 2 to H2O on the product side. So that's just to show that essentially if you take your time, and in most cases if you save oxygen and hydrogen for last, balancing a chemical equation is not the worst thing you can do. So let's go on to some other types of chemical equations we can work with. And we'll get into next week naming these different types of reactions. Like the first one is a metathesis or single displacement. We'll work on those guys. So let's work on balancing the single displacement of zinc and hydrochloric acid, forming molecular hydrogen and zinc chloride. As always, to balance out a chemical equation, just right from the start, assume you have a 1 coefficient in front of every chemical compound, and then just count up how many of each element that gives you. So on the reactant side, we are currently looking at 1 zinc, and similarly we have 1 mole of zinc on the product side. As far as chlorine goes, we only see 1 chlorine on the left side, and for zinc chloride, ZnCl2, we have a subscript of 2 next to chlorine. Therefore, that means that that molecule counts for 2 chlorine atoms. And as far as hydrogen goes, we have 1 on the left side, and the only place that hydrogen shows up in the product side is with molecular hydrogen. Therefore, that would count for 2 moles of hydrogen. Now to start balancing this guy. Well, zinc is already balanced because we have 1 mole of zinc on both sides. Therefore, what seems to be the issue, and I see I put that should be a 1 on the product side for hydrogen. So what it appears is that chlorine and hydrogen on the reactant side are both 1, whereas there is twice as much hydrogen and chlorine on the product side. Therefore, let's add a coefficient to HCl that essentially multiplies the numbers by 2, which we can just add a coefficient of 2. Therefore, adding a coefficient in front of HCl does not affect zinc's amounts, but on the reactant side we currently have HCl, which has 1 hydrogen and 1 chlorine, and we just add a coefficient of 2, so timing each number by 2 we get 2 hydrogen and 2 chlorine atoms. And simply by adding a 2 in front of HCl and not adding a coefficient in front of anything else, we now have a balanced chemical equation because we have 1 zinc on both sides, we have 2 moles of chlorine on both sides, and we have 2 moles of hydrogen on both sides. Therefore, we're obeying the law of conservation of matter. Nothing is being lost or coming out of thin air. Everything is accounted for. Now let's go for a decomposition reaction. Again, we'll get into names of these next week. But as far as this week, let's just worry about balancing chemical equations. Here we have a nice decomposition reaction, and for metal carbonates or metals that have a CO3 anion as part of the compound, these break up into nice metal oxides and carbon dioxide molecules. As always, let's just count up the number of each element we have on both sides. As far as lithium goes, since the molecule on the left is Li2CO3, that means we have 2 units of lithium on the left side. And since lithium only appears on the right side as part of Li2O, that molecule has 2 amount of lithium as well. As far as carbon goes, we only see 1 on both sides. And for oxygen, we see that Li2CO3 on the reactant side, that 3 is a subscript of oxygen. Therefore, we have 3 oxygens on the reactant side. And on the product side, we have oxygen appearing in both compounds. So for LiO, that is 1 mole of oxygen. And for CO2, we have 2 moles of oxygen. Therefore, the total amount of oxygen on the product side, without adding any stoichiometric coefficients, is also 3. Therefore, this reaction is already balanced. We don't need to add any coefficients because all the elements are already balanced. And sometimes you will see problems like these where you don't actually have to add any coefficient. Now let's get on to a combustion reaction. These are essentially you're taking a hydrocarbon, so a molecule of carbon and hydrogen, and sometimes oxygen too, and reacting it in the presence of oxygen. And these kind of reactions always form CO2 and H2O, so carbon dioxide and water. Now, same trend as always, let's just count up how many of each element we're starting out with and see which ones are not balanced yet. So carbon only shows up on the reactant side for C4H8. Therefore, there are 4 carbons on the reactant side. And for the product side, we only see 1 mole of carbon because of carbon dioxide. Going on to hydrogen, C4H8 carries with it 8 moles of hydrogen. And on the product side, we have water, which only has 2 moles of hydrogen. And lastly, we have oxygen to think about. On the left side of the equation, we have O2, therefore that's 2 moles of oxygen. And on the right side of the equation, the product side, we have CO2, which has 2 moles of oxygen, and then H2O, which has 1 mole of oxygen. Therefore, 2 plus 1 is going to give us 3 moles of oxygen. Now, it appears that everything is pretty much not balanced. And that's crazy. So what we should think about doing is balancing the number of carbon first. Usually hydrogen and oxygen, you want to save those guys for last. So in this case, if we have more carbon on the reactant side, then let's add a coefficient on the product side to balance out the number of carbon. And if carbon is only showing up in CO2, and therefore we only need to add a coefficient in front of CO2. Now, if we want to have a total number of 4 carbon on the product side, and each time we add a coefficient in front of CO2, that's adding 1 mole of carbon. What times 1 gives you 4? Well, 4. So adding a coefficient of 4 in front of CO2 now brings us up to 4 carbons, but adding a coefficient in front of CO2 affects the total number of oxygen on the right side of the equation. Therefore, what we're actually looking at as far as oxygen goes is CO2, so 4 times 2 oxygen, which is 8, plus the 1 oxygen in water. So that's currently 9 oxygens. Now, next thing we can worry about balancing is actually the number of hydrogen. If we have 8 hydrogen on the left side of the equation, and the only place that hydrogen shows up on the right side is through H2O, we can easily add a coefficient that multiplies by 2 to give us 8. Therefore, we're going to add 4 in front of H2O, which should give us 4 times 2 hydrogen, or 8 hydrogen. And now this affects the total number of oxygen again. So we have, from CO2, we have 4 moles of carbon dioxide. So 4 times 2 oxygen, which gives us 8, plus 4 moles of water. So 4 times 1, which is 4 moles of oxygen. So in that case, we have 8 plus 4, or a total number of 12 oxygen. Now, what it appears is that carbon and hydrogen are both balanced. Yet for oxygen, we have much more moles of oxygen on the product side than on the reactant side. However, on the reactant side, the only place that oxygen shows up is in O2. And if we have an even number of oxygen on the right side of the equation, then balancing the left side is going to be pretty easy. What times 2 will give you 12? Well, 6. So adding a coefficient of 6 in front of O2 is going to give us a total of 12 oxygen. And therefore, we now have a fully balanced chemical equation, and a combustion equation at that. Now, this next equation is a common acid-base neutralization equation. We'll get into naming chemical equations, but this one, again, we're just focusing on stoichiometry, and there are quite a lot of players to think about here. So starting out with how much of each we have, just counting up the number of sodium on both sides, we have 1 on both sides of the equation. And as far as chlorine goes, we have, once again, 1 on both sides. For carbon, we have 1 on both sides as well. Now hydrogen is where we are going to count up 1 from the first reactant, which is HCl, and then 1 from the second reactant, which is sodium bicarbonate, or baking soda. Therefore, we have 1 hydrogen plus 1 hydrogen, 2 total hydrogen on the left side of the equation. And on the right side, we have 2 hydrogen just through H2O. Alright, well this is looking pretty cool. It looks like so far everything is already balanced. So last but not least is oxygen. On the left side of the equation, oxygen only shows up in sodium bicarbonate, which each molecule or each mole of sodium bicarb carries with it 3 oxygen. So we'll just have 3 oxygen as the total number on the reactant side. And on the product side, oxygen shows up in both water and carbon dioxide, water having 1 unit of oxygen and carbon dioxide having 2. Therefore 1 plus 2 equals 3. Alright, cool. So this is another example of a chemical equation that is already balanced. We don't need to add any stoichiometry to it to balance any of the elements. Now, one thing I should note is that technically, let's say we added 2 in front of each of these compounds, in front of each of these chemicals. Technically, if we added 2 in front of all these, that would still be valid. We would still have the equal amount of each element on both sides. We would just have everything multiplied by 2. So 2 sodiums on both sides, 4 hydrogens on both sides, 6 oxygens on both sides. Cool. In reality, though, you go with the least common multiple of each number. So, for example, if each coefficient that you wrote in your chemical equation can be divided by, say, 2, then you would divide each by 2. Or if you could divide each by, say, 3, then divide each by 3 until you get the least common factor, least common multiple. That's why we don't add any coefficients of 2 or anything else. We just use the least common number, which in this case, to balance everything, we just need to have 1. And we don't need to show 1. So cool. Now these next few guys, these are just more practice. For these, for bromine, for BRF, reacting to form molecular bromine, which is Br2, and BRF5, well, this one's going to be a fun one. On the left side of the equation, we have 1 bromine because of BRF. And on the right side of the equation, we have a molecule of Br2, therefore there are 2 bromines from that. But BRF5 carries with it 1 bromine as well. So that would be 2 plus 1, which is 3 moles of bromine. And on the left side, we have 1 fluorine, and on the right side, we have, because the only place that fluorine or F shows up on the product side is through BRF5, and F has a subscript of 5. That means that without adding any stoichiometry, we are at minimum working with 5 bromines. Now, how to balance this chemical equation? Well, might seem pretty tricky at first. My suggestion is, since we have a molecule of bromine that will always be even on the reactant side, and we have a molecule of BRF5 on the product side, which fluorine could be odd or the total number of fluorine could be even, depending on how much you add. My suggestion is just add a coefficient in front of BRF5, just so that we're working with even numbers. So I'm going to add 2, a coefficient of 2 in front of BRF5, and that changes the total number of bromine and fluorine on the right side of the equation. Therefore, with fluorine, we have BRF5. 2 times 5 is going to give us 10 fluorine. And as far as bromine goes, we have still no coefficient in front of Br2, therefore that's 2 bromine. And for the coefficient in front of BRF5, that's going to take 1 bromine times 2. Therefore we have 2 plus 2, which is 4 bromine on the left side, on the right side of the equation. Now, just to balance out the number of fluorines on the right side of the equation, on the left side of the equation, adding a coefficient of 10 to BRF is going to give us 10 fluorine, but it's also going to give us 10 bromine on the product side as well. Now then, let's see what we can do to balance out bromine on the product side. Well, Br2 is the only thing we haven't added a coefficient to yet. Therefore, what we want is to have a total number of 10 bromine on the product side. And right now, we already have 2, because we have a coefficient of 2 in front of BRF5. And let's not worry about adding a different coefficient. Let's see what coefficient we can add in front of Br2 to essentially give us a total number that, when added to 2, gives us 10. So, in other words, if what times 2 then plus 2 gives you 10? Well, 10 minus 2 is 8. Therefore, what we're going to need is something times 2, which gives us 8, or just 4. 4 in front of Br2. Therefore, what we have on the product side is 4 times 2 bromines, which is 8, plus 2 times 1 bromine, which is 2. Therefore, we have 8 plus 2, which is 10. Cool. Now, like I said earlier, what you want for coefficients is actually the least common multiple. So if there's a common multiple, in this case 10, 4, and 2, each can be divided by 2. We're going to want to do that instead. So 10 divided by 2 is going to be 5. 4 divided by 2 is going to be 2. And then 2 divided by 2 is going to be 1, which we don't need to show 1 because it can just be assumed. So, in doing so, we now have a balanced chemical equation which has 5 of each element on both sides, and the stoichiometric coefficient in front of each chemical compound is the least number needed to basically balance out that chemical equation. So just a few more examples. One more, which would be, say, sodium reacting with inorganic phosphorus, or P4, to form sodium phosphide. Assuming we are only working with 1 mole of each from the start, 1 mole of Na gives us 1 sodium on the reactant side, and 1 mole of sodium phosphide will give us 3 sodiums. Whereas for phosphorus, 1 unit of P4 carries with it 4 phosphorus, and on the product side, we have sodium phosphide, which has 1 phosphorus. All right, something to think about. Sodium on the reactant side is all by itself, and no matter what number we put in front of Na, it's going to be that number times 1. Therefore, balancing out sodium in the end should be pretty easy. Therefore, let's look at a number that would allow us, let's worry about balancing out phosphorus then. Well, on the reactant side, we have more phosphorus than we do on the product side, because we have 4 phosphorus on the left side, we have 1 on the right side. So now we should think of a coefficient that we can add in front of Na3P that would give us a total of 4 phosphorus on the right side of the equation. So if Na3P only has 1 unit of phosphorus, what times 1 is 4? Well, 4. Therefore, we now have 4 moles of phosphorus on the product side, but on the product side we now have 4 times 3, which is 12 units of sodium. How is that number obtained? Well, sodium has that subscript of 3, and a coefficient multiplies everything in the chemical compound it's attached to. It multiplies everything by that coefficient. So if we have a coefficient of 4 and sodium has a subscript of 3, 4 times 3 is 12. Now, to basically balance out sodium, well, that's easy. If we just have 1, no matter what coefficient we have in front of sodium, timesing it by 12 will just give us 12 times 1, or 12. Therefore, we have 12 sodiums on both sides, and we have 4 phosphorus on both sides, just by adding coefficients of 12, 1, and 4 in front of our chemical compounds respectively. One last example, one last thing to drive this home, is essentially boron trichloride reacting with water to form boric acid and HCl. So this is another acid-base equation. Adding up the total number of each element we have on both sides, there is currently 1 boron, 1 B on both sides. And for chlorine, BCl3 carries with it 3 chlorines because of the subscript. And on the right side of the equation, there's only chlorine only shows up in HCl, and HCl has 1 chlorine. Therefore, that has 1 on the product side. Hydrogen, we are going to see that water carries with it 2 hydrogen on the left side, and boric acid has 3 units of hydrogen, and HCl has 1 unit of hydrogen. Therefore, 3 plus 1 is going to be 4. And last but not least, oxygen, which only shows up in water on the left side of the equation, carries with it 1 oxygen, and oxygen only shows up in H3BO3 on the right side. Therefore, 1 molecule of that carries with it 3 oxygen. And what appears to be the issue is that chlorine, hydrogen, and water or oxygen are both not balanced yet. So, saving hydrogen and oxygen for last, if we have 3 chlorine on the left side, we can add a coefficient of 3 in front of HCl in order to have 3 chlorines on the left side of the equation. Now this affects the total number of hydrogen, therefore we have 3 hydrogen from boric acid, and we have 3 hydrogen from hydrochloric acid, HCl. Therefore 3 plus 3 is going to give us a total of 6 hydrogen on the right side of the equation. Now then, we have a balanced amount of boron and a balanced amount of chlorine. Now we can focus on hydrogen and oxygen, which luckily both only appear on the reactant side in H2O, and the reactant side is what has less amounts of each compared to the product side. Therefore, we probably can kill 2 birds with 1 stone here. For H2O, each molecule of H2O carries with it 2 hydrogen. Therefore, if we want a total number of 6 hydrogen, what times 2 is 6? Well, 3. Therefore, we now have 3 times 2 hydrogen, which is 6 hydrogen. That is now balanced. And since that affects the total number of water, or oxygen, for the reactant side, we have 3 moles of water. Each mole of water has 1 oxygen, so 3 times 1 is going to be 3 oxygen. And there we go. Just by adding a coefficient of 3 in front of water and a coefficient of 3 in front of HCl, hydrochloric acid, we now have a fully balanced chemical equation. And just for an assignment to do for the rest of this week, by this Friday, which would be the 27th, if you guys essentially email me balanced chemical equations for these guys with bismuth, then I'll give you some extra credit. +2 if they're all right, plus 1 if they're mostly right. So yeah, why do I have bismuth showing up here? Well, it's actually my favorite element in the world. It's has like a beautiful metallic chrome rainbow to it, and I love it. But essentially, your assignment for the rest of this week, by Friday, just balance out these 3 chemical equations. We're going to be doing a lot more balancing throughout the semester. So here's a good start. Balance out these 3 chemical equations and email me your answers by Friday, and I'll count it as extra credit. Just going on, some things that I didn't mention yet is that sometimes you will see a chemical equation that has the physical state attached to it, which is essentially little subscripts that aren't numbers. And while I don't require you guys to remember this, I just want to show you it. Essentially, if you see a subscript of G, that means that that chemical compound is in the gas state. And then L would be in the liquid state. If you see a subscript of S, that means that that chemical compound is in the solid state. And then if you see AQ, that means that that compound is aqueous. And essentially what that would mean is that, say you had sodium chloride, aqueous, that essentially means that you have a molecule of sodium ions and chloride anions that are together. So if you see an aqueous compound, aqueous just means that that molecule is in its individual ions as opposed to a single compound. Just some things to note as far as the remainder of this semester is that there have been some changes on administration's end. And those changes are essentially that midterm grades are going to be pushed back instead of this Friday, are going to be pushed back to Friday, April 10th. And as far as your last day that you can drop or withdraw without getting a failing grade is Friday, April 24th now. Therefore, essentially, you have until the last 2 weeks of class to basically drop the course if this online format is not working out. And essentially, you will have your third exam by then, and you will know your third exam's grade by then. And essentially, the only thing left after April 24th is going to be one more slideshow of lecture material, and then your fourth exam. So you will have a pretty good idea of most of the material for the fourth exam before the last day to drop, and you will have a good idea of where your grade is at by that time. And this is just a little slide of the upcoming lectures. Since we are online, I'm going to focus on a week's worth of material as one lecture slideshow, which I will upload on Monday. Today we did stoichiometry. Next week will be types of reactions. And then Wednesday of next week, I will give you access to your third exam as well as the extra credit practice exam. And while that will be available starting April 1st, it's not due until April 10th, end of day Friday. And then and then the week afterwards, we'll get into some gas laws. And then if there's some time, we'll briefly cover some nuclear chemistry and some organic chemistry. And then by April 29th, you will have access to your final exam, or well, your fourth exam. We do not have final exams. Therefore, since your last day to drop is Friday, April 24th, you will have a pretty good idea of your grades and what will be on the last test by that drop date. And that's it for this week's lecture. Just get in those extra credit chemical equations if you so choose. Otherwise, enjoy the rest of your week, guys.